Okay, so while this projector I think needs to cool down or something, it's not turning on. So I'm just going to start with the thing we were trying to finish with last time, which we didn't have time to cover, which was we had this this function we're interested in. It's the distance to a convex set C. So you give me a point x, and this measures the distance between that point x and a convex set C. In other words, it's the smallest distance between an element of C and x. And I claimed last time that, well, first of all, we know this function is convex, right? Let's see if that works. First of all, we know this function is convex from one of our earlier classes. And second of all, I claimed that the set of subgradients of this function actually only contains one element. So that must be its gradient. That was what we ended with last time. I tried to give you some intuition for the proof of this last time, but I don't think it stuck. I think it's kind of a hard thing to explain intuitively, so we're just going to go through the details. You'll see that it's not too complicated, but it's worth going through so you can see how we might prove, for example, that that thing is a subgradient of the distance function. Great. So we're only going to do one direction, by the way. I'm only going to prove that this element is a subgradient of the distance function. I'm not going to prove it's the only one. And like I explained last time, usually that's good enough for our purposes. Usually we just have to find a subgradient of some function. We don't have to characterize all of them. So it's not really of our primary interest at this point to prove that that's the only subgradient. Okay, so let's go ahead and do that. Okay, so the first thing I'm going to do is I'm going to define the element of C, assuming that C is closed, the element of C that lies closest to x. Okay, and I'm going to call that U, and U is going to be the projection onto C of x. That's how we're going to write it. Okay? In other words, U solves this problem. Minimize overall U in the set C. Say the squared distance between U and x. We don't need to worry about the square. I could have just put the norm there too. So first of all, let me ask you guys a question. Is U unique? Is there only one point that's closest to x? To x in the set C. I see some no's and some yeses. So the answer is yes. Why does somebody think the answer is yes? C is convex, yeah. What do we know about convex optimization problems, say in terms of the uniqueness of their solutions? Use a solution to this problem. What's a sufficient condition for the solution to be unique? Strict convexity, yeah. Is that a strictly convex function? In U? It is, right? It's a quadratic. So it's definitely strictly convex. I think usually like the first few minutes of class, everyone's just waking up maybe. But I think you guys all believe me on that one. Okay, so this U is uniquely defined. And we already know, for example, from the first order condition for optimality, that let's call this f of U, this criterion function f of U. And I'll put a half in front. It doesn't really matter. All this stuff doesn't matter. It doesn't change the solution, right? It's just going to be for convenience. We already know the first order definition of convexity is that the gradient at the solution, right, inner product with, say, y minus u, has to be positive for all y in the set C. That's the first order definition of characterization for optimality, right? We actually proved this, by the way, from the subgradient optimality rule last time. So you guys saw how this came about. Okay, so let's apply that here. What's the gradient of this function with respect to u? You guys should eat breakfast. I think it would help with the math in the morning. I'm just teasing. What's the gradient of that? You guys know the gradient with respect to u. What's the gradient of this function with respect to u? U minus x, right? Okay, so this is our first order characterization for optimality. In other words, if u satisfies this, we know that u is optimal, and vice versa. Okay, so this is actually the characterization for the closest point u to x in the set C. Okay, so now we're going to say that let's define a half space, H, which is a set of all y, such that this thing is positive. Right? We're going to just consider u to be the projection of x onto C. That's fixed. X is fixed. And now we're going to consider the set of all y such that u minus x transpose y minus u is non-negative. That's a half space. Okay, it's going to look something like this. It's going to be all this region. Okay, so if we draw this vector u minus x, this guy here, and we draw y minus u for any other point y in the set C, like say this one, the inner product between the two of them is positive, right? The half space contains all positive inner products. So we know that C is contained in this half space, right? Just from this condition that we derived. Okay? Okay, now I'm going to claim the following, which is that for any y, the distance between the point y in C is going to be bigger than or equal to what happens when we take this quantity and we normalize it. By its leading inner product. Okay, and you're going to see where that comes from. Let's just go ahead and check this directly. We'll do two cases. The first case is when y is in C. Actually, sorry, when y is in the half space. So why is that true when y is in the half space? Take a look at this quantity here. Yeah.
The distance between y and C.
Yeah, that's right. If y is in the half space, what do we know about this quantity? By the way, we define the half space. Look, this is x minus u, and that's u minus x. So if y is in the half space, then this right-hand side is negative. Right, by definition of the half space. So that's fine. The distance between a point and the set C is always positive, non-negative. This is going to be negative when y is in the half space, so that's fine. That case was easy. How about when y is in the not in the half space now? Okay, so now we're going to consider a point y, say out here.
Is this the distance between y and u or y and C?
This?
Yeah.
Distance between y to C, y and C. Okay. So if y is not in the half space, then we're going to notice that x minus u transpose y minus u, I can always write as x minus u times y minus u in norms times the cosine of the angle in between these two vectors, x minus u and y minus u. Okay, so now I'm considering x minus u and y minus u, so I'm going to flip the direction of this arrow because I flipped the direction of that vector. Okay, and this is the angle between them. Okay, so that's true, and therefore if I divide by x minus u in norm, it's just equal to y minus u times the cosine of the angle in between these two guys. Okay, I claim that this is the distance between y and the half space. Why is that true? You can see it directly from the picture. This is the distance between y and the half space, right? From some of our basic geometry facts, you'd believe that this angle between y minus u and x minus u is the same as this angle. Right, you guys can all see that. And so what's y minus u times the cosine of theta? Look, it's just the distance between y and the half space. Okay. All right, so now we've shown that this quantity, which is the mysterious quantity I had on the right-hand side, is actually explicitly the distance between y and the half space. The half space contains c. So clearly the distance between y and c has to be bigger than or equal to the distance between y and the half space. Right, if you look at this picture, the distance between y and c might be something here, but the distance between y and the half space is going to be smaller than that. Okay, so this is less than or equal to the distance between y and c. Okay, so now I've established this claim. And if you look at what this is saying, we've actually directly proved that the quantity in question is the subgradient of the distance vector, of the distance function. Why? Let's just expand the right-hand side of it, and remember that the distance function is the one that we're interested in. So this is f of y, right? We said this is bigger than or equal to. Let's pull out, let's do x, say minus, and this, let's expand this out, x minus mu transpose, let's do y minus x plus x minus u over x minus u. So all I've done is I've added and subtracted x in here. Let's expand that out. And we get, see, the leading term is just going to be equal to x minus mu in 2 norm. Right? What's that? Remember, that's the distance between x and c. So we can call that f of x. And the other term looks like this. X minus u divided by its norm transpose y minus x. And we're going to call this g. And what we established is that this is true for all y. So actually what we've established in this claim is just the fact that this vector g is a subgradient of the distance function at x. Okay? Any questions about that? Okay, that was just a demonstration of how to prove something's a subgradient. I believe that if you walk through these steps backwards, you would also be able to show this is the only subgradient of the distance function. In other words, you'd be able to show the distance function is actually differentiable if we're measuring the distance to any convex set. And that's a pretty nice fact because I didn't tell you anything about C, right? I didn't tell you C was smooth. And if you had tried to approach that, say, from other principles, from the principles of calculus that you learned in, say, previous courses, that might have been a pretty difficult thing to prove. Okay, so I'm going to take that lack of questions as a sign that you understood this, but make sure to speak up if something's unclear.
What is the projection of a point to set that contains a point that's 0?
The distance?
So the projection, what is the projection on y on say c in case where y is in?
So we have to ask two questions. So the first, what's the closest point? Suppose x is in the set. What's the closest points to x that's in the set? It's itself, right? Okay. So then what's the distance between x and the set? It's just 0.
If C is not convex, it's still differential.
Well, if C is not convex, then the projected point itself need not be well defined, right? So uniqueness is a pretty special property of convex sets, right? So for example, suppose this were my set. Then what's the closest points to x and C? There's multiple, right? So I think the answer is generically no, but I'm not.
But it's just the distance in.
Yeah. Okay, so actually I believe it's true. Now this is getting somewhat outside this topic, so maybe I'll just state this and then we can talk about it afterwards if you're interested. I believe it's true that for any set, convex or not, the set of points that have a non-unique projection has measure 0. I think that's true in general. So I would venture a guess that it's differentiable almost everywhere. But that I'm not positive. It's a good question. Okay, so that was the end of our subgradient lecture. We're going to jump right into subgradient method now. So this is the second algorithm you guys have learned so far. You've learned gradient descent, which I assume that most of you knew or saw before. This one probably not. So this might be the first new algorithm you learn in this course. And then we're going to obviously go from here. You guys are going to learn lots of algorithms to put in your toolbox. So last time, just remember, actually last time, not last lecture, but the lecture before, the one that Mattia gave, Mattia covered gradient descent, which was an algorithm for minimizing a smooth convex function without constraints. Okay, and we assume that this function has domain all of Rn. That's what we assumed in the gradient descent lecture. And the steps, remember, were just to repeatedly take steps in the direction of the negative gradient. So you make some initial guess, x0, and then you iterate by finding the gradient at xk minus 1, and then moving a small step in the direction of the negative gradient. And these step sizes were chosen to be either fixed and small, or by backtracking line search. Those are two strategies that we learned. If the gradient was Lipschitz, under this assumption, so this was Lipschitz continuous, we showed that if the step sizes were chosen to be less than or equal to 1 over the Lipschitz constant, so if the Lipschitz constant is L, we have to take the step sizes to be 1 over L or smaller, then this converges to the solution and has a convergence rate 1 over epsilon, which means that the number of iterations needed to achieve an error of epsilon in terms of the criterion value that you're visiting and the one that's optimal scales like 1 over epsilon. So what were the downsides? The two downsides were that it requires f to be differentiable. We're going to actually overcome that this lecture by using subgradients. The second downside is that it can be slow to converge. So you may need many iterations to get within a good distance of the optimal criterion value. Okay, and we're going to talk about that next lecture. So let's just jump right into the subgradient method. The subgradient method takes the same setup, except for we don't assume that f is smooth. So f is convex, its domain is all of Rn, but it's not necessarily differentiable. So like gradient descent, we're going to iterate by making some initial guess, and then at each step we're going to try to compute not the gradient, but the subgradient of our criterion at the current iterate, wherever we are. And so it's really the same form as gradient descent. You can see a strong analogy here, except for instead of taking the gradient of our criterion function at the point xk minus 1, we just take any subgradient. So really any subgradient. If the function f is non-smooth, it could have many subgradients. We can take any of them at this point, and we can use that subgradient in this iterative fashion to try to descend on the loss function. Okay, so really it's really all you'd expect once you knew gradient descent and you learn subgradients. Just replace gradients by subgradients. So here's one difference. We're going to see many differences between subgradient method and gradient descent in this lecture. Here's one difference. Subgradient method is not necessarily a descent method. So actually I've been careful to call it subgradient method and not subgradient descent, although you might catch me slipping a bunch of times and calling it subgradient descent. Which means that as we iterate along the steps of the algorithm, we may actually ascend on the loss rather than descending on the loss. With gradient descent, we've proved that for a small enough step size, that wasn't possible. That was actually in the proof of convergence of gradient descent. One of the things we showed was that if we took the step size to be smaller than or equal to, say, 1 over the Lipschitz constant, the gradient, then we actually get a sufficient descent condition. Not true for subgradient method. So what we do is we actually continue iterating along the sequence. We don't worry about the fact that we could be ascending on the loss. But we keep track of the best iterate we visited so far in terms of its criterion value. So we just keep track of the lowest criterion value achieved along the whole history of iterates. And then after suppose we iterate for 1,000 iterations, we consider our approximate solution to be the one that had the smallest criterion value. Not necessarily the last one. Questions? Okay, so here's the outline for today. We're going to talk about how to choose step sizes. This is really actually analogous to what we did for gradient descent. How to choose step sizes. We're going to talk about the convergence of subgradient method. We're not going to prove its convergence. That we're going to skip. We did that for gradient descent. We're going to skip that for subgradient method. We're going to talk about applications of subgradient method. In particular, we're going to see that there's a nice intersection of sets problem we can solve with subgradient method. And then we're going to talk about a stochastic version, which is pretty interesting considering kind of the large-scale problems that we want to solve in modern data analysis. And we're going to revisit stochastic methods at the end of the course, probably as an advanced topic, where we'll talk about them in more detail. So how do you choose the step size in subgradient method? Well, there's two ways to do it. The first is to choose the step size to be fixed, like gradient descent, just fix it at some level t, so that it's the same magnitude across all steps of the algorithm. The second is to choose them in some diminishing fashion, so that they get smaller over steps of the algorithm. And there are various ways to do this. There are various prescriptions for how to do this. This is one that's easy to remember. It's called square summable but not summable. So remember that distinction, which means that we want to make sure the step sizes, when we square them and add them up, they're finite. But when we add them up, they're infinite. So in other words, we want to make sure that the step sizes go to 0 over steps of the algorithm, but not too fast. Right? Because bigger step sizes means more progress, so we're kind of trying to balance those two things. Go to 0, but not too fast. Here's one precise way to make that statement true. We want to enforce that, say, the step sizes, like I said, have an infinite sum, but when we square them and take their sum, they're finite. So what's an example of a step size rule that satisfies those two conditions? That's right. I could just take tk to be 1 over k, and I would satisfy those two conditions. Okay, so that's a pretty common one that you'll see people choosing in applications of subgradient method. And we'll see exactly why we want this to be true in a second. So the big difference between this and gradient descent is that we don't have a notion of backtracking for subgradient method generically. So all the step sizes in subgradient method are not dynamically chosen based on kind of where we are along the iterations of the algorithm. We don't look at the problem and try to dynamically choose a step size like we do in backtracking. They're all pre-specified. So that's one big difference between those two methods. Here's the convergence results for subgradient method. And like I said, we're not going to prove this. Let me see. Actually, the proof is in the slides, so you guys can take a look at that if you're interested. And we're just going to analyze something at the very end of the proof that is going to give us some insight as to why we have those step size rules. So if f is convex, its domain is all of Rn, and f is Lipschitz. So remember, in gradient descent, we assumed that the gradient of f was Lipschitz. Here we're actually assuming that the function itself is Lipschitz. It's a different assumption. We don't have a notion of a gradient, right, in subgradient method. So we're assuming the function itself is Lipschitz with a constant capital G. Right? Remember, that means this. The difference between f at x and f at y is at most g times the distance between x and y. Then we have the following two results. The first is that if we fix the step size t, subgradient method in the limit is suboptimal by an amount g squared times t over 2. This was the Lipschitz constant of the function. So if we use a fixed step size, we're actually not going to get necessarily the optimal criterion value in the limit as we carry on steps of the algorithm for an arbitrarily long amount of time. But it'll be suboptimal by this amount. You can see the smaller the step size, the smaller this gap between f star and the best achieved criterion value along the sequence of subgradient method iterates. If we choose the step sizes to be diminishing according to that rule we saw, which means that the step sizes, again, their sum is infinite, their squared sum, or the sum of their squares is finite, then in the limit we actually do get the optimal criterion value. Okay, so this says it's convergent. It doesn't tell us what its convergence rate is yet, just that it converges. So I'm going to skip through this proof. I just feel like it's not a good use of our time. But I definitely encourage you to go through it to make sure you understand the kind of basic steps of the proof, because they all come from the basic convex analysis techniques that we've learned so far. Okay, all the stuff that we've learned so far, that's all you need to understand this proof. We're just going to go to the end of the proof, where we establish something called the basic inequality. Which is that we said that after k iterations, assuming that the criterion is Lipschitz, the difference between the best, I guess I switched these compared to the slides, but it doesn't really matter, the best criterion value that we've seen so far is at most some number r squared plus g squared times the sum of the step sizes so far, squared step sizes, divided by the sum of the step sizes seen so far. So this was a bound that we established through that method of proof that I'm skipping. This is called the basic inequality for the subgradient method. R, by the way, is the distance between our initial point, say x0, and a solution. Just to keep the notation consistent. Okay, so now we can actually, from this, we can read off the results for the convergence analysis that we saw directly. Right? Let's take let's first take tk to be t. So let's look at the fixed rule. Then this bound, the bound is just r squared plus g squared times, this is just k times t squared, right? Divided by 2 times k times t. If all the ti's were just equal to t. K, which is equal to r squared over 2kt plus g squared times t over 2. So as we take k to infinity, that goes to 0. And we see that the suboptimality between subgradient method's best iterate and the optimal criterion value is at most g squared times t over 2. Came right from the basic inequality. Now let's take the diminishing rule. So let's take k to infinity. Right? We see that the limit as k goes to infinity of fxk best minus f star. Well, let's just take the limits in each of these quantities separately. The first one is going to be r squared over the limit of this sum as k goes to infinity, so the infinite sum of the ti's. That's infinite by assumption. So it's r squared over something infinite, so the first term is just 0. Second term, remember the denominator goes to infinity by assumption. By assumption, this is finite. Right? So something finite over infinity, so the second term is also just 0. So that's the bound we get in the limit, which means that subgradient method converges to the optimal criterion value. Okay. There's something else we can get from this bound. This basic inequality is very useful, and that's the convergence rate of subgradient method. We've seen that we can prove convergence, but we haven't actually talked about its convergence rate yet. And this is going to be a big distinction between what we get with gradient descent and subgradient method. And again, let's just go to the basic inequality, and let's ask what we need. Let's suppose we're using fixed step sizes, because that's the easiest analysis. But we can do this with diminishing or other choices as well. I'm just going to do fixed step sizes because it's easiest. Let's just suppose we want the bound to be at most epsilon. Okay, and we're going to see how do we have to choose t and how do we have to choose k to make this work. So we're going to try to make each term smaller than epsilon over 2. So there's two terms here. We're going to achieve this bound to be less than epsilon by making each of these two terms smaller than epsilon over 2. Okay, so remember, the step size was fixed. So we're going to make the first term smaller than or equal to epsilon over 2, we have to make r squared, this is the first term, divided by 2 times k times t less than or equal to epsilon over 2. And we also want to make, it was g squared times t over 2 less than or equal to epsilon over 2. If we make both of those two things true, then we've established the criterion value is at most epsilon. The difference in criterion values is at most epsilon. So this tells us that we have to take t to be at most epsilon over g squared. Right? And the bigger the t, the better. So it just tells us to take t to be equal to epsilon over g squared. And now this tells us as a result that we have to take k equal to r squared. No, is that right? Yeah, that's right, sorry. So now let's rearrange this. And this tells us we have to take k to be at least r squared over 2k epsilon. Right? I'm just rearranging this to get an inequality. That should be a t. 2 times t times epsilon. And now let's plug in for, it's just t times epsilon. There's no 2. The 2's canceled. Let's plug in for t. That says k has to be r squared times d squared over epsilon squared. Okay, so in order to make the criterion value be at most epsilon from optimal, we have to take t to be on the order of epsilon, and as a result, the number of steps we need is on the order of 1 over epsilon squared. So in other words, the convergence rate, right, the number of iterations needed to be within epsilon of the optimal criterion value is on the order of 1 over epsilon squared. Okay, so now you might come to a point where you said, well, look, all you did was you made sure that that was true by choosing k and epsilon, k and t, and by using fixed step sizes. So how do I know that's the best that you can do? Right? This might have been a loose analysis. I just said, well, let's just make the first term smaller than epsilon over 2, the second term smaller than epsilon over 2, and that's what we needed. And I also used fixed step sizes. So you might think that this might be loose, right? There's no reason to think this is actually necessarily the tightest convergence rate. But this is the tightest convergence rate. And I'll show you a theorem at the end that kind of confirms that. Okay, so there's two answers. The first, that you could try this for diminishing step sizes or other choices. You'd see you end up at the same result. And there's a second answer that says that actually we'll see that this is the best you can do in some sense if all you're willing to assume is that the function is convex but non-smooth. So this is really the convergence rate of subgradient method. Okay, so compare this to gradient descent, right? Gradient descent had 1 over epsilon. This is a rather big difference, right? Suppose we wanted epsilon to be, say, 10 to the minus 3. We wanted 0.001. We want to be within 0.001 of the optimal criterion value. Then this says we need how many iterations for gradient descent, for example, to get that, on the order of how many iterations? 1,000, right? And how many do we need here? What's that? 1,000,000. Yeah, 10 to the 6. So that's a pretty big difference between the number of iterations required, say, for gradient descent and subgradient method. Okay, here's an example just to show you that this kind of thing presents itself in practice also. I took, as a problem setting, I took a classification problem where I had predictor variables xi and I had binary outputs yi. So I wanted to predict the class being 0 or 1, from a bunch of predictor variables. And I used a logistic regression loss to do so. So I hope that you guys, how many people are familiar with logistic regression? Just nod your heads. You should have seen that in, say, 701 and other classes. Right, so we've been talking about linear regression in a few instances so far this class. This is another kind of canonical problem form where the outputs are binary rather than continuous that you're trying to predict. Is this convex? Let's answer that question first. Have we done this already? I can't remember if we actually have done this already in this class. Have we already done that? This example? Maybe not. Is this a convex criterion? Well, look as a function of beta. Let's look at this part. What is this as a function of beta? It's linear. Okay, so that doesn't matter. How about this? Sum from I equals 1 to n of log of 1 plus e to the xi transpose beta. Is that a convex function? We learned that, right? That's the log sum of exponentials. That's a convex function, certainly. So this is convex, and its gradient looks very much in line with what we see in linear regression. In linear regression, we saw that the gradient was the predictor variables interproducted with the residuals. It's the exact same thing here, except for the residuals here are yi, the output, minus, instead of just being xi transpose beta, like it would be in linear regression, it's the predicted probability of yi being equal to 1. Right? And in the logit model, that's just exactly this. It's 1 over 1 plus e to the minus xi transpose beta, or e to the xi transpose beta over 1 plus e to the xi transpose beta. Those two things are the same, the things I just said. So this is an exercise for you to check if you're unfamiliar with where that came from, or if you're unsure of that. Take the gradient of this loss function, it's this. Okay, so now I'm going to consider a regularized problem where I'm doing logistic regression, but I'm also going to apply some kind of penalization or regularization. And I'm going to do it in two ways. One in which the problem ends up being smooth, and one in which it ends up being non-smooth. And we're going to do subgradient method on the non-smooth one, gradient descent on the smooth one, and we're going to see how they converge. So for the smooth one, I'm going to do a ridge penalty. So it's an L2 squared penalty, which is going to push all of the components of beta towards 0. And these are the coefficients of the predictors, right, in the classification model I'm building, beta. And in the other one, I'm going to use a lasso penalty, an L1 penalty, which actually pushes coefficients of in beta to 0 exactly. We know that kind of intuitively. We've talked about that in linear regression, I think, a couple times at least already. So this guy is, if I add lambda, which is some penalty parameter, some positive fixed constant, plus the squared L2 norm, then the total criterion, f plus lambda times the L2 norm squared of beta, is still convex and it's smooth. If I add the L1 norm, it's convex, but it's non-smooth, right? The L1 norm is not smooth. It has, we know this from the last lecture, if I'm ever along a coordinate axis, like if I look at the ith component of beta, then when that's 0, the L1 norm is non-smooth. Just like the absolute value is not smooth at 0. So here's the two methods compared side by side in the same data instance. And I try to make this as fair as possible. But of course, it's kind of hard to do because these are two different problems I'm solving. But at least it gets the point across. I took 1,000 observations and 20 predictor variables. So not a huge problem. It's not a high-dimensional problem. But it's a decent-sized problem at least. And I applied gradient descent and subgradient method. And I tried to hand-tune the step sizes in each case to make the algorithms converge as favorably as possible. And what I'm plotting is, on a log scale, the difference between f and the optimal criterion value for the ridge penalized problem where I can apply gradient descent, and for the lasso penalized problem where I have to apply subgradient method. At least so far, we don't know how to minimize the lasso penalized logistic regression problem with the methods that we've learned unless we're using subgradient method. Because all we have in our toolkit is gradient descent and subgradient method, and it's not differentiable. So you can see there's a big difference in how these guys converge. Just superficially, right? In terms of the shapes of these convergence curves. And you can see that for a... So I took two choices for subgradient method. One was diminishing, where I took it to be 0.001 over k. That's the red curve. When you can believe this is going to continue going down, right? When I took it to be a fixed step size, 0.001, you can see it looks like it's probably stuck around this point. It's not going to get any better. Okay, we're going to see a much better way to solve this logistic regression problem with an L1 penalty next time that actually recovers this kind of convergence behavior. But so far, if all we know is subgradient method, we're kind of stuck with this regime of convergence. So here's another choice of step size that I want to mention. It's kind of an interesting one. They're called Poliak step sizes, but I'm sure that if you were Hungarian, you'd pronounce his name differently. Last year I had somebody in the class who was Hungarian, and she corrected me, but I can't remember exactly how to pronounce this. But I'm saying Poliak. And it's an interesting choice of step size when you know the optimal criterion value. So suppose we know f star. That's, not going to happen all the time, but believe me, it happens sometimes. I'm not saying we know the solution. That'd be different. Knowing the actual optimal solution would be kind of defeating. There'd be no reason to run subgradient method. But if we know what the criterion should be at optimality, that's a little different, right? That happens in some cases, and I'll show you a case in which that happens next. If this is known, then we have a different choice of step size, and it looks like this. We take the distance between where we are right now in terms of our optimal criterion value, f of xk minus 1 minus f star, and we divide by the squared norm of the subgradient that we see, again, at the current iterate. If you go back to the first step of the subgradient proof, we use this bound. So this bound came from just plugging in the definition of xk in terms of xk minus 1 minus tk times the subgradient. It's just the rule for xk, expanding the square, and then using the definition of a subgradient. That's where this bound came from. I didn't go through the proof, but like I said, you should step through that if you're curious after class. This choice of step size is what minimizes the right-hand side, so it makes the bound as tight as possible when f star is known. That's one way to motivate it. So had we done the convergence analysis, we would have made that bound in the first step, and we would have said, what's the step size that makes this the right-hand side here, which is bounding the distances that xk is from optimality, as small as possible. It's one way to motivate it. So if you just say differentiate this with respect to tk and set it equal to 0, you'd get this expression for tk. So even with this like kind of somewhat idealistic choice of step size, which is only possible when we know the optimal criterion value f star, you can show the convergence rate is still 1 over epsilon squared. So it doesn't really do us any better in terms of the convergence rate, but it is the best step size in some sense practically if we know the optimal criterion value. So I'm going to go through an example of where we know the optimal criterion value, and where we're going to plug in the Polyak step sizes, and you're going to see something kind of interesting coming out. And the problem setup is as follows. Suppose we have m convex sets, C1 through Cm, and they're closed and convex. And we want to find a point in the intersection of these sets. So why might we want to do that? Well, that might be the problem itself we're trying to solve. Or, for example, we might be trying to initialize our convex optimization algorithm. Suppose we learn an algorithm later in class that requires us to initialize the first iterate to be feasible. This might be this might define the feasible set for a convex optimization problem. C1 might be the set of all x for which g1 of x is less than or equal to 0. C2 might be the set of all x for which g2x is less than or equal to 0, and so forth. And we're going to learn problems for constrained convex optimization as we go through the course. If we want to initialize a point for an algorithm for constrained convex optimization, we often have to make sure the initial point is feasible. So if we don't know how to do that analytically, we might have to run something like this to get something that's close to feasible. Okay, so how are we going to do that? Let's just first define fi of x to be the distance between x and any of these sets ci. So we've seen that function before. We studied it at the start of class. And we're going to define f of x to be the maximum of fi of x over all I going from 1 through m. So this is the maximum distance that x is to any set ci in our collection. And now we're going to solve the problem minimize over all x, f of x. If those sets have a non-empty intersection, if C1 through Cm have a non-empty intersection, which we're assuming, then we know that the optimal criterion value here should be 0. Right? Because there should be some x that makes it so that this maximum is 0, which means that the distance between x and every set is 0, which means that x lies in every set. So it lies in their intersection. So this is a case in which if we know that the sets have non-empty intersection, then we know the optimal criterion value. It should be 0. Okay, just to continue with this kind of these basic questions, because we're going to see this stuff throughout the course. Is this a convex criterion that we're trying to minimize? Each one of these fi's is convex. We know that, right? Maximum of convex functions is convex, so yes, it's a convex problem. Okay. We're going to actually solve this problem by subgradient method now. That's how we're going to approach it. And we're going to derive the subgradient method steps for minimizing this criterion, the maximum distance between x and any set ci. And in fact, we already know how to do this, really. It's just using the steps doing this are using two things we've already learned. One is how do you take a subgradient of the maximum of convex functions? We learned that last time. And the other is what are the subgradients of the distance function, which we talked about last time in the start of class. So really we know how to do this problem. And in fact, like I said, we know that the distance function to any convex set, I'll just write it down for you one more time. We know that the subgradients of this guy between a point and any convex set, this contains one element, and that looks like this. It's the difference of x and its projected point onto the convex set Ci divided by the norm of that difference. Okay, so in fact, because there's only one element, we learned that this was the gradient. We're not even going to use here that actually we need this to be the gradient. So this is an example of where if we just knew that the subgradient contained that point, that would be good enough. But just for simplicity, I'm going to write it as the gradient. But you'll see, we don't actually need this to be differentiable. Now what's the subgradient rule, right? The subgradient rule, if I have a bunch of convex functions, the rule for the subgradient of the maximum of these guys, remember we learned, was look at all the I that are active, which means that fi of x is equal to f of x. Right, it achieves the maximum. Take all the subgradients of fi at x, take the union over all active functions, and then take the convex hull of this. Because we know that the set of subgradients of any convex, or of any function is convex. Right, the subdifferential of any function is convex, then we know that these are all valid subgradients, then so must be their convex hull. It's the rule that we learned. And you're going to actually prove that on the homework, I believe. So let's apply it to this function. So we're saying that the subgradient is equal to the union over all I such that Ci is farthest from x. So what does it mean for fi to achieve the maximum value f of x in the context of our problem? Right, these were remember the distances of x to Ci. Well, if the maximum is achieved at Ci, it means that Ci is the farthest set from x. So there could be multiple, right? It could be a tie between some sets. That's why it's a union. We look at all the sets that are farthest from x. We collect all of their subgradients. Their subgradients are just these guys, right? That we proved. And we take the convex hull of that. So that's the subgradient of our loss function. And in order to get a subgradient, what could we do? Well, there's actually not much. We don't have to worry about the union of the convex hull. All we need is a subgradient in order to apply subgradient method. So all we have to do is actually find a set that's farthest from x. So find one of the sets Ci that's farthest from x if there's a tie. Just take that. That's a valid subgradient for the function f of x overall. Okay, so that's going to lead us right into the subgradient method now for minimizing this loss function f. It's just repeat the following steps. Right, find I such that Ci is farthest from x. We're going to take Gi, or take G rather, just to be the subgradient given by the distance function between x and Ci. From what we know up here, this is a valid subgradient of our criterion function. So the subgradient method is going to form the following update. I'm going to write x plus, which I often do, to denote the next value of x in our iteration. I just don't want to use the k notation because it's a little bit, I think it's just simpler to use this for this example. So I'll go back and forth between that. To be x, which is where we are, minus a small step size, t, times this subgradient, x minus p Right? That's our subgradient iteration, subgradient method iteration. And if I just took any fixed step size t, small enough, then we know that we'd approximately minimize f, right? Let's take a more special choice of t and see what happens. Let's take the Polyak step size. That was the point of this example. Right, that was equal to, that was telling us to take t to be the criterion value at x minus the optimal one divided by the norm of g squared. What's the criterion value at x at this step? It's the farthest that x is from any one of those sets. So that's actually equal to x minus it's projection onto Ci in norm. Because remember, Ci was chosen because the set was farthest from x. So that's equal to f of x. F star is 0 if we know that there's a point that's in their common intersection. And what was the norm of g? Remember, g was this. So what's its norm? Its norm is just 1, right? Norm squared is 1. So in other words, the Polyak step size tells us to take t to be equal to the distance we are currently to the farthest set. And so what does that mean? It means that x plus is equal to where we are, x minus, the denominators cancel, right? I'm doing x minus PCI of x times x minus PCI of x divided by x minus PCI of x. These cancel. And you can see that what we end up with is just x minus the projection of x onto Ci, which is just the projection of x onto Ci. So let's recap. What is this? This is just a subgradient method applied to that criterion function, which is a maximum of distances to all the sets. Once I took the Polyak step size, which I could apply in this example because I knew f star. F star was 0. It's pretty simple in this example. This is actually a really natural algorithm. What is it telling us? So let's just go back to that first step. Find I such that Ci is farthest from x. What does my next update look like? It's just given by projecting x onto Ci. So I'm just finding the farthest set from x, projecting onto that set. The next step, I find the farthest set from x, I project onto that set. I find the farthest set from x, I project on that set, etc. That's just an alternating, it's called the alternating projections algorithm. So this is quite an old algorithm itself. Right, for two sets, it just looks like this. Suppose we wanted to find intersection between those two sets. We just start with some x. We project onto say C1, because suppose C1 was farthest from x. Then the next step, C2 is going to be farthest from x, right? Because distance between C1 and x is 0. So we project onto C2, project onto C1, project onto C2, etc. until we find a point in their intersection. With multiple sets, the story is similar. So that's pretty neat, right? Because this is a very natural algorithm. You may have actually thought of that on first principle if somebody asked you to solve this problem. Seems like you could have come up with that. But what if somebody asked you, does this converge, and how fast does it converge? That's actually not a very easy question to answer, right? You think about maybe analyzing the properties of this geometrically or something. But we know what the answer is because we know it's a subgradient method. The answer is that it does converge, right? If we take these Polyak step sizes, we know it does converge. And its convergence rate is 1 over epsilon. So if we want to be within epsilon of every set, then we're going to need 1 over epsilon. Sorry, its convergence rate is 1 over epsilon squared. If we want to be within epsilon of every set, we're going to need something like 1 over epsilon squared iterations. If I have the history right, maybe Javier can correct me on this if I have it wrong, but I think this is right. I believe this is Dijkstra's algorithm for alternating projections. Do you know? Okay, well I'm going to claim it is then, and maybe I'm wrong. But I believe this is Dijkstra's algorithm for alternating projections. And von Neumann has another algorithm for finding the intersection in sets that we're going to see is actually can be derived from ADMM, which is an algorithm we'll learn later. So there's a better way to even do this problem than this one, but this will do the job at least at this point. Are there any questions about that? Yeah.
What if the sets were really close but not intersecting? And so the step size that you take, so f star is not really 0. So there's some error in the step size that you ended up taking. You still reach the minimum, but it's not a constant step size.
Yeah, it's a good question. So just to repeat the question is what if the sets were really close but didn't intersect, so the f star was now actually 0, but we took the Polyak step size anyways? I don't know the answer to that question off the top of my head, but I have to believe that it would work in some approximate way. So basically, with regards to almost everything that we're talking about in class in terms of convergence analyses, there are analogs of these results for, say, noisy situations where we get the gradient wrong by a little bit, or we get the subgradient wrong by a little bit. And I think what you're talking about might fall into this category, right? I can interpret that as maybe, well, yeah, I guess I can interpret that as a little bit of noise in the subgradient, because I could absorb t into the subgradient and talk about the subgradient being a little bit too big rather than the step size being off. So I think that it would work in some approximate sense, but the details I don't know off the top of my head. It's a good question.
Does the size of the solution set relative to the size of the domain affect convergence?
Good question. So let's go back to the bound and see if we can answer that question. So here was the bound we derived. All right, this was the bound between the best iterated after k iterations and the optimal criterion value. And so the question that was asked was, does the size of the solution set play any role in the convergence rate, convergence analysis? So it doesn't play a role in the convergence rate, but it does play a role in terms of the constants in that convergence rate. Because look at r here. R is the distance between our initial point and x star. We can take r to be actually the distance between the initial point and any solution. So this bound is valid for any solution x star. So if there are many solutions, r might be smaller, right, than if there's one solution. And so this appearance of r on the right-hand side would be smaller. And actually, we saw that the convergence rate, wherever I put that down, it was r squared times g squared over epsilon. So as a rate in terms of epsilon, it didn't change, but the constant's smaller. You can see that r is just going to be smaller there. It's a very good question. Any other questions? Okay, let's take a very quick break, like a couple minutes, and then we're going to do stochastic subgradient method when we get back, and that'll be it. I want to make sure that we get through the stochastic stuff because it's pretty cool. I'm not going to go through it in in a lot of detail because we're going to hopefully revisit at the end of the course, and we're going to talk about some developments on stochastic methods as well, recent developments. This stuff is quite old, so I'm telling you about right now. So this is also a topic that's interesting because I'd say people in optimization who are in optimization kind of properly are aware of these stochastic or incremental methods. They're called either thing, really. But the people who are most interested in them are the people who do machine learning and statistics because these problems are very prevalent in those fields. So I think most of the interest and probably most of the application of these methods comes from statistics and machine learning rather than optimization proper. Although this stuff, like I said, the stuff I'm talking about today is pretty classical optimization theory. Later in the course, we'll revisit it and talk about some more modern theory that comes out of ML and stats. So we're going to be in a situation now where we're considering a sum of functions. So instead of optimizing a single f of x, we're optimizing a sum of fi of x. Right? Oftentimes we might think of f as a sum of functions. When is that true? Well, that's really true almost any time we're doing some kind of empirical risk minimization, right? Or we're actually building a loss function over, pair m here would be the number of data points n, say in our data set. So an example of this is linear regression, right? I can always write linear regression loss or least squares loss like that. So these would be my FIs of beta. I equals 1 to n. Another example is the classification loss, where it was something like this. This logistic loss. Again, this is my FI of beta. So we see a lot of problems like this in statistics and machine learning. And typically, if we're solving, so I'd say modern problems, we have n quite large. So there's a lot of elements in this sum. And let's think about applying the subgradient method, say, to a criterion that looks like a sum of functions fi. So we're going to say f of x is equal to the sum of fi of x. And we're going to think about applying subgradient method here, or gradient descent. Really, either is fine to consider, but let's just consider subgradient method since that's what we're talking about today. So in order to do this, we have to compute a gradient or a subgradient of f. But we know from from the subgradient calculus rules, or even just gradients, that to do that we have to compute subgradients or gradients of each of the fi's. And then we have to sum that over all I. So in this setting I have I going from 1 to m. This might be very expensive if m is large. So in other words, to take a single subgradient step, looking back at the slides, I have to do xk minus 1 where I was, minus tk times the sum of subgradients gi going from 1 to m, where gi is a subgradient of fi. This just comes right from the subgradient calculus rules, like I said. This whole sum is a subgradient of this whole sum of functions. All right, so that the motivation is that could be very expensive, right? It might be very expensive to compute this sum. So there's an alternative approach we can use called stochastic subgradient method, or incremental gradient method, subgradient method, which instead of computing the sum, just takes one of these subgradients. And it chooses one of them according to some rule. So again, I'm going to choose some index ik from 1 to m. I'll tell you how to do that in the next slide. And I'll just take the subgradient of that function fik and allow that to describe my update rather than the sum of subgradients, called stochastic subgradient method. So just peek at that for a second because it's an important distinction. Okay, of course, when f is differentiable, right, if each of these is differentiable, then what I'm really saying is that instead of computing the sum of gradients of fi, I'm just going to choose one of those functions, compute its gradient, and move along the direction of that gradient, rather than the sum of all the gradients. That would be stochastic gradient descent. This is a special case of this. So here are two rules for choosing an index at iteration k. The first is a cyclic rule. So that means I allow each function in my sum to tell me where to go in turn. So I ask function number 1, give me your subgradient, I'll follow that. Function number 2, give me your subgradient, I'll follow that, etc. And then I go back and repeat in a cyclic fashion. Another possibility is a randomized rule. So I'm going to choose the index at each step uniformly at random. I'll just pick uniformly among all of my functions at random, and I'll update along their subgradient or gradient at random and repeat. So what's the difference between stochastic and the usual subgradient method, which we usually call batch subgradient descent? In the context of stochastic methods, if we end up computing the full sum of subgradients or gradients, we call it the batch method. Well, from a computational point of view, if you look back at their differences, right, m stochastic steps is equivalent to one batch step in terms of the number of computations needed, right? Because I'm really having to compute one subgradient per update in the stochastic rule and m per update in the batch rule. So computationally, if I take m stochastic steps, that's the same as one batch step. First of all, even if those two progressed in the same way, why might it be advantageous to use a stochastic method? Let's suppose that all I told you was that all you get out of stochastic methods is that in terms of the progress you make on the optimization criterion, it's the same if you take m stochastic steps versus one batch step. Why might we still want to use a stochastic step versus a batch method? If I told you computationally they're the same, because m stochastic steps is one batch step, and also in terms of the progress are the same. I claim there's still utility in them. What's that? Yes, that's right. So memory is the short answer. So if I didn't have the full data set in memory, because suppose memory was an issue, which may be the case if m is enormous, maybe even more so than computation, then I don't have to have the full data set in memory each time I run a step. For example, for the randomized rule, or even let's say for the cyclic rule, I could just load, say, one of those FIs into memory at a time, compute its subgradient, move along that direction, and then push it out of memory and load the next one in. So even if we didn't get anything else from it, it's already worthwhile, as long as the progress is the same as a batch step over m steps. But we're going to see there's actually more to them than just that. Let's do a very rough calculation in the case of differentiable. So let's suppose that each fi is differentiable for now. And I'm going to try to convince you from the perspective of just writing out the stochastic steps that we might believe that we do get the same efficiency as one batch step after m stochastic steps. So just like I said, a really rough calculation. And let's suppose we use the cyclic rule, and we're going to take a constant step size t. So after, suppose we start at step k, right? After m stochastic updates, I claim that what I'm going to get is this update. Okay, so in other words, let's just look at the progress after one step, stochastic step. I'm going to do xk minus t times the gradient of the first function in the cyclic rule. So I take the gradient of f1, and I'm going to evaluate it at xk. So that's k plus 1 minus 1. The second step, we're going to go from there, and we're going to add along the gradient t times the gradient of f2. And then going to evaluate that at xk plus 1. That's the second term in this sum. So I equals 2. And then we're going to add the gradient along f3, and so forth. So after m steps, if we collect all of those updates just in one equation, this is what it looks like. Okay? So this is the stochastic rule. How about the batch rule? What does the batch rule look like after one step? Well, of course, we know this, right? This is just gradient descent. I have to put here the gradient of f at the point xk. And because f is the sum of functions, it's just the sum of fi's. The gradients of fi's at xk. So what's the difference between these two rules in this kind of simple setting? It's that the gradients in the stochastic rule are kind of evaluated at the wrong places. They're just wrong in the sense that we know that gradient descent converges, and so we're trying to make this look as much like gradient descent as possible. They're just being evaluated at the wrong places, that's it. instead of each of these being evaluated at xk, they're being evaluated at x k plus I minus 1. So, I can write this guy as xk plus m is xk minus t times the gradient of f at xk plus some capital E, which stands for error. That error is just going to be the difference between these two functions, right? Which I've written out in the slides here. This is the error. It's the sum over all the functions of the gradient of that of fi evaluated at say xk plus I minus 1 and xk. So here's actually kind of, in a sense, referring back to something that was asked earlier. We might think of stochastic gradient descent as a noisy version of gradient descent, where instead of applying the proper gradient at each iteration, we apply the gradient plus some perturbation, epsilon, E. And if E was small, we might believe this would still work, right? We'd still get the same kind of convergence properties as gradient descent. And let's look back at the terms of E. This looks like Fi when I take its gradient at xk and xk plus I minus 1. And xk plus I minus 1 is going to be close to xk if the step size is small. And if the gradient behaves nicely, suppose it's Lipschitz, then we could apply a bound on this term directly, and we might be able to use kind of some of our work on the convergence for gradient descent to prove this converges as well. And that's in fact one very basic way to prove that the stochastic methods do converge. Okay, so that's just supposed to be a bit of insight into why you might think it converges. Okay, I'm right at the end of time, so I'm just going to show you a picture, and then we're going to come back to this at the start of the next class. Here's the picture. So here's the takeaway point, and I'll give more detail next time. It's often much better to use the randomized rule than the cyclic rule. Why? Because the randomized rule actually makes more progress on average. So in the randomized rule, we can apply about an average case bound, so that on average, we do very well with the randomized rule. In the cyclic rule, there's no real way to protect against worst case behavior. And in the cyclic rule, in the worst case, we're no better off than we were using the full batch method. So it's equivalent in terms of its progress to the full batch method. The randomized rule on average, we do much better. And this is kind of the classic picture that you might see if you see people applying stochastic methods, which is that I've run two versions of gradient descent here. One that's batch and one that's stochastic with the randomized rule, choosing a random function to optimize over to follow the gradient each time. And gradient descent in blue, you can see it follows the contours, the gradient kind of nicely, passing through the contours to the optimum. The stochastic method appears to make a lot more progress, but then it kind of bounces around the neighborhood of the optimal solution. So the rule of thumb for stochastic methods in general is that they strive far away from optimum, so they make a lot more progress than batch methods away from optimum, but they struggle when you're close to optimality. They don't converge to high accuracy. It's just something to remember when you're looking at a very large problem that you're trying to optimize. And we'll talk about this in a little more detail next time. So, okay, the homework 2 should be posted later today, hopefully, and I will see you guys on Monday.